So the first part of the course is actually about how to use databases, and in this course, except for the probably last week of the course, we're going to be using relational databases. So today, we're giving you an introduction to the relational database model, and specifically the part that corresponds to what we call the data definition language. Then on Thursday, and for several lectures after that, we will be focused on the data manipulation language part of the relational model. So today's kind of just getting into the relational model, into the structure of it, getting definitions and terms down is the big deal, and then a few characteristics of it. So today, well, actually to show you, so the current chapter, chapter 4, covers how you create the structure of a relational database. So it will map later to what we call the data definition language. Then starting with chapter 5 or 6, it's going into the query language, actually chapter 6 I believe, which is how we insert, delete, update, and read information from the database. So today, we'll get definitions and terms, we'll get characteristics of the relational model, and then we'll get constraints on the relational model. So this is what a relational model looks like. Basically, the database is a set of tables. And in this course, the running example used in the book is a property management company. So these two tables, there's a branch table which lists all the branches that we have for our company, and a staff that lists all of our employees. And as you can see, each table across the top has named columns. So the names of the columns are the attributes. So we call each column an attribute. And the entire table is called a relation. And the number of rows in the table is called the cardinality of the relation. The number of columns is called the degree. So you can see here degree, that refers to the number of columns. Cardinality is the number of rows. Okay. So each while every cell, so we talk about cells in the table. So a cell is the intersection, is a particular value of an attribute in a particular row. So for example, here 22 Deer Road is the value of that cell. It's the value of the employee B005, or I'm sorry, the branch that is located at 22 Deer Road. And you'll see in a bit that there's restrictions on attributes. The two most important restrictions on attributes is that they have, for a particular column, they must all be drawn from the same domain. So for example, you can't mix strings and integers in a column. It has to be all strings, all integers, all dates, etc. The second big restriction is there can be only one value per cell. You're not allowed to have multiple values. So for example, you don't see phone number here, but you would not be allowed to have multiple values for a phone number. Or for staff number, you don't see children listed, but if children were listed, it would not be legitimate to have multiple children listed. You could have only one child listed. You might say, well, how do you handle that? We'll talk about that later in the course, but that's one of the major restrictions in the relational model, is that you can have only one value per cell. And then you see some other things. You see here primary key. So primary key is a group of attributes that uniquely identify each row in a table. And we have these definitions on subsequent slides, so you don't have to try to write all of this down. But a primary key set of attributes that uniquely identifies each of the rows in a table. So in this case, the primary key is the branch number for the branch relation and is staff number for the staff relation. So one thing that often happens with primary keys is that they're artificially derived, meaning it's a some kind of identification code. Your social security number is an example of an artificial or artificially generated key. Whereas your last name, even though it's kind of in some sense artificial, it's considered more of a natural key, something that's innately part of you. And then you see the second thing, foreign key. So a foreign key is what allows us to join the information in two different relations. So for example, if we wanted to find the street address at which John White works, what we would do is see that John White works at branch B005, so we could use that foreign key, that's called a foreign key, to go to the branch relation. In the branch relation, that foreign key is the primary key, and when we look up the street there, we see that John White down here is working, the street address for John White is 22 Deer Road. So these foreign keys are the glue that allows us to kind of navigate through different tables in order to find additional information that's not contained in the current table. It's almost like a pointer. If you're familiar with pointers, it's almost like a pointer into another table that gives you access to more information. So foreign keys are going to be primary keys in another relation in the database. So questions about any of this? This is actually already given you most of the basic terminology for a relational database. Yes?
Are these usually sorted by the primary key?
Generally. So the question was, are they usually sorted by the primary key? And actually, I should take that back. There's usually what is called, we'll get to it, a secondary index that sorts them, but usually they are not sorted on the primary key. Usually they are sorted on a different key. And so we'll get to this, but just the quick answer is that there is what are called range queries, where you want all rows or tuples between some value. Like you might want all people whose last name starts with S, okay? So generally a range query is on some kind of like innate or natural attribute. It's not going to be on an artificial thing like a primary key, because primary keys are artificially derived. It really doesn't make sense to say, I want all branches whose primary key is between B5 and B7. So actually, while the primary key is a unique identifier, believe it or not, they're usually sorted on a different attribute, because the one you sort on is normally one that's conducive to what we call a range query. Okay, but we don't have to worry about that right now. A range query is just one that returns a whole group of records in a range. Other questions? Okay. So, I mean, I'm going to skip over this stuff. I'll let you, the slides are posted so you can look at the definitions. I've already told you what the definitions are so you can look through them. The domains are pretty much what you would expect, but in databases there is a couple domains that you may not, well, that are not common in programming languages, at least traditional programming languages. So dates are a common type in a database. I know they're also common in scripting languages, but you won't find a date as a built-in type in C or Java. Same thing for monetary values. There are some databases actually have monetary value types, whereas you certainly wouldn't find that in a regular language, even a scripting language. But otherwise, you have the normal types: integers, floating point numbers, strings, characters. Even sometimes you can store things like binary data, but it turns out that you often store the binary data in separate files and have pointers out to them. And in this course, we're not going to worry too much about binary data. Okay, it's not one of the strengths of the relational model is storing things like images. It's not a strength. Okay. Pardon? So oftentimes you would just have the name of an image file. So instead of actually storing the entire image file in the database, you would just say like bvz.jpg. So you would have a file name, and then the file would be stored off separately. Would be the more normal way to do it. Because otherwise you're kind of bloating up your database. And because things like my picture file or your picture file might be used in different places in a system, it's often good just to have it as a separate file. Okay. This one slide you do want to pay attention to. Okay. So the reason you want to pay attention to it is because each of the terms we've talked about, relation, tuple, and attribute, has 3 different ways of referring to it depending on who you are. So if you're an academician, you probably use the formal terms on the left. You probably say relation, tuple, attribute. But if you're an end user and you're communicating with an end user, you probably are using the terms in the middle. So instead of saying relation, you use the word table. Instead of using the word tuple, you use the word row. And instead of using the word attribute, you use the word column. And in this course, you will hear me use the terms interchangeably. That's why I say it's important you kind of commit this table to memory, because sometimes I'm going to say table, sometimes I'm going to say relation. You need to know that they're the same thing. And I'm just kind of, my brain at that moment is thinking relation, and 5 minutes later it's thinking table. Okay, and then the third way you will hear them referred to is for the people who design the database or who write the database software. They're thinking in physical terms often. So to them, they'll often call a relation a file. They'll often call a tuple a record in the file, and they'll often call an attribute a field in the file. In fact, those are the 3 terms you're probably familiar with from your undergraduate or graduate level courses. You probably think of files, records, and fields. So that's an important table. Memorize the different relationships between those terms, because you got to become kind of fluent in just seamlessly shifting between relation, table, file, or between attribute, column, and field, knowing that they're the same thing. Okay, time for the eyes to glaze over for a moment. No, you need to pay attention, but this is the mathematical part of it. So I sometimes get questions from students, why do we even care about the mathematics of it? It's because most of you are computer science majors, and because this is not Palisippi State. If this was Palisippi State, we would not be covering the mathematical foundations of the relational model. But as computer science majors, you should know what is the mathematical underpinnings of this thing, okay? Some of you may go on to graduate school and need to do more advanced work with relational databases. Some of you may go to work for a company like Microsoft or Oracle that actually creates the software, and for that, again, it helps to know the mathematical underpinnings for the relational model. So, and it's also why 311 is required for this course, because relations roughly correspond to the relations you learned about in 311. So, roughly speaking, consider 2 sets, in this case D1 and D2. So D1 is a domain, it has the values 2 and 4. D2 is a second domain restricted to the values 1, 3, and 5. So then the Cartesian product of those 2 domains is what you see right here. It's 6 pairs of numbers. Okay? So that would then become, if we had a 2 attribute relation whose first column was chosen from domain D1 and whose second column was chosen from domain D2, then this would be the universe of possible tuples for that particular relation. So the relation would be some subset of these tuples. It would be rare for it to be all of them. In the real world, the universe of tuples is nearly infinite, okay? So you can think of a 30-character field for street address. There's, what, 26 to the 30th power just for lowercase. So, I mean, the number of tuples is, for all intents and purposes, infinite, the possible. But we always are taking some concrete subset. Okay? So it's rare that you, quote, have a finite set. I mean, in practice, there's always a finite set. It's just so big that as to appear infinite. So in this case, R is a particular instantiation of this relation. So in particular, it has those two tuples drawn from the possible space of tuples. And in practice, the way we specify a relation is by enumerating all the tuples in the relation. So in practice, we use approach Roman numeral 3 there. But in theory, there is another way to specify a relation, which is mathematically. So rather than enumerating the tuples in the relation, you could give a definition of it. So I could say that R is the set of tuples such that X is in domain 1, Y is in domain 2, and Y is equal to 1. So essentially, it's a set of all values that we can take from domain 1 and cross product with the value 1. So the domain 1 was 2 and 4. Therefore, there are two tuples in R, 2, 1, and 4, 1. Okay? Or here's the second one. It's a set of a second relation S drawn from our universe. It's a set of tuples such that X is equal to 2 times Y. And the only possible tuple that satisfies that is 2 and 1. Okay, if you look at any other thing, 2 times 3 is 6, which is not in domain 1. 2 times 5 is 10, which is not in domain 1. So there's only one tuple that satisfies that mathematical definition. So again, in practice, we always enumerate concretely all the tuples, but you should know that you could theoretically just provide a mathematical specification of the tuples. And then it would just be all tuples that match that specification. So then you can scale that up to 3 tuples. I won't do that here. And finally, you scale it up to the general case where you have n attributes. So each attribute has a domain. You take the Cartesian product of those n domains, which is usually written this way. Hopefully you've seen that multiplication symbol before. So it's just from I equal 1 to n, the Cartesian product of those domains. And then a relation is any subset of n tuples from that Cartesian product. So that's the mathematical underpinning of it. Definitely not quite as intuitive as just drawing a table with a bunch of columns, but you should know it. Okay, now another couple terms that you need to know. So we talked about relation, attribute, tuple. Then there is relation schema and relational database schema. So remember on Thursday we talked about a database catalog where a user could look at the catalog and it would list the names of the relations, and for each relation it would list the names of the attributes and their types. So the information that names a relation and the set of attribute domain pairs for that relation is called a relation schema. So when you hear the term schema, usually people don't say relation schema. Normally they just say schema. What they're in effect referring to is like the variable declaration, the class declaration in a program. They're referring to the name of that relation and the attributes in that relation and their types, their type information. So a schema is essentially type information about a relation. And then a relational database schema is the set of relational schemas for a database. So it's just the union of all the schemas. Okay, so the big word you have to remember here is schema, and know that's essentially the type declaration for a relation. Okay, so we've given you the terms. Now there are some properties of relations, some restrictions, if you may, on relations, many of which are pretty obvious. So the relation name should be distinct, pretty obvious, right? Otherwise there's going to be ambiguity when you refer to a relation. I'm going to skip to 3 because 2 is not obvious. 3, each attribute has a distinct name. That should be pretty clear too. If you have 2 columns in the same relation with the same name, then it's going to be pretty confusing when you say, if you have 2 relations with the field name, it's going to be pretty confusing when I say, well, the name of the staff person, you're looking at me, well, there's 2 names, right? So you can have the same column name in 2 different relations. It's fine for the branch relation to have a field called name, and it's okay for the staff relation to have a field called name. But within the same relation, you can't have 2 columns with the same name. That should be pretty obvious. 4, the values of an attribute must all be drawn from the same domain. So that's a lot like most programming languages. Most variables, when you declare their type, that's it. That's the values are drawn from that domain. Now, scripting languages are different. Scripting languages, a variable can assume values of different types at different points in the program. Okay, can't do that in a relation. When you declare the schema for the relation, you specify the type of the attribute. It's got those values from then on. Okay, 2, that's the one that's not obvious. That's more arbitrary. Okay, but it simplifies a lot of operations in relational databases, and so they chose, this is more of an operational thing. It makes it a lot easier to handle many of the operations that are performed on relational databases. So they restrict each cell in a relation to contain a single atomic value. So that's what I meant by you can't have multiple phone numbers, you can't have multiple children, 1 value per cell. That's probably the most important thing to remember. Okay, then each tuple is distinct, so you can't have duplicate rows in a relation. That is not always easy to do, and that's one of the reasons why you often generate artificial keys to identify people, because there are so many people in the world. If you have a staff relation and you have some fields like name, street address, even salary, you could end up with a duplicate. So one reason you have artificial keys is that sometimes it's the only thing that makes 2 tuples distinct in a relation. So that's a hard and fast. After the 1 value per cell, the each tuple is distinct is the second one that may not be so intuitive. Okay, third thing, and this is where things diverge from 311. Okay, so in 311, you were probably told that the order of the attributes in a relation had significance. So if you had a relation where you had attributes A1 and A2, that was different from a relation where the attributes were in the order A2, A1. That's not true in a relational database. The order of the attributes has no significance. So these 2 relations would be considered the same relation. Yes.
Cells, I know you said you only could put 1, I guess it's 1 thing in the cell.
Yep, 1 value.
Put a list, say you declare a cell
No, you can't. So that's the issue. Okay, you could fake a list, like you could, when I say fake a list, right, you could try to do something like Brad, hashtag Nils, who's my brother, hashtag, right, so you have an artificial, but it looks to the database system like it's one string. Okay, so when the database system looks at it, it thinks it's just one value. Now you have encoded it, but any encoding you do is yours, okay? So no, you can't do lists. And that's one of the things that NoSQL lets you do. It lets you store lists in your fields, and that's one of the big advantages of NoSQL. Other questions? Okay. Final thing. So the order of tuples in theoretically has no significance. So just like the attributes has no significance, the order of the columns, the order of the rows, in theory, has no significance. As the gentleman asked, though, earlier, do you sort the tuples in practice? And the answer is yes. In practice, you generally sort the tuples on one or more of the attribute values. But from a theoretical standpoint, the order of the tuples is meaningless. So two relations that have the same set of tuples but in different orders would be considered the same relation. Okay, so if I had one relation, relation 1 had attribute A1, A2, values 5, 8, and the next one 6, 2. Relation 2 was also A1 and A2, and its were 6, 2, and 5, 8. Relations 1 and R2 would be considered the same, identical relations, because the order of the tuples is not significant. Okay, pretty easy. Basically, what you want to remember, one value per cell, tuples are distinct, are the big two. Okay, the other 5 we went through 7 properties. The other 5, I think, are pretty intuitive. Okay, we kind of went through keys earlier when we talked about primary keys and foreign keys. So again, a primary key uniquely is a set of attributes. Actually, let me give it here. I didn't have, okay, go back. So a primary key is a set of attributes that uniquely identifies each tuple within a relation. And it's the one chosen for that relation. So we'll get to it in a moment. So there are a number of terms you'll hear for keys. You need to know all of them. So we start out with a super key, which is an attribute or set of attributes that uniquely identifies a tuple within a relation. I know I was earlier saying that's also a primary key, but basically we then talk about candidate keys, which are keys that uniquely identify all tuples in the relation, and if you remove any attribute from that key, then it no longer uniquely identifies all the tuples in the relation. So it's the minimal possible set of attributes that identifies a the tuples in a relation. So here's one that you will see a lot in the homework assignment. So we have 4 relations. This is a schema. So hotel has hotel number, hotel name, city. If this was a true schema, what's it missing? Gave you the definition. There's one element missing from the schema. Pardon?
The address.
Not the address. Sorry, we're not talking about actual. You're right. A hotel would normally have an address, but there was something in the schema. It contained 3 elements, and there's only 2 elements here. Missing the domains. So I'm giving you the name of the relation and the name of the attributes, but you're missing the domains. So it's not actually a complete schema. But you can probably infer what the domains are. So normally, when you see us give schemas in this course, we omit the domains because they're usually pretty obvious. So we have one that represents the hotels in our chain, one that represents the rooms in each hotel. Type of room might be like a double or a king size or the penthouse suite. Bookings are the reservations for our guests, and guests is a directory of all of our guests, not just guests currently staying in the hotel, but who have stayed at any time. So it should be clear, for example, from the hotel relation that hotel number is a super key for hotel, and guest number is a super key for guest. You actually might not be able to guarantee that hotel name and city by itself is unique. For example, in the city of Knoxville, there are multiple Holiday Inns. So if you say Holiday Inn, Knoxville, there are multiple Holiday Inns. That by itself is not unique. Same thing, you could have two guests, father and son would be the most likely, with the same guest name at the same guest address. But it gets more interesting when we talk about room. So with room, there is no single attribute that uniquely identifies the room, because it turns out that we are talking about all rooms in all hotels. So you could have the same room number, like 303, in two different hotels. So that's not going to uniquely identify the tuples in the room relation. And similarly, within a hotel, the same hotel, you could have multiple rooms. So what do you think might be a super key for, or a candidate key rather, for room? Louder. Room number and hotel number. So a super key for room would be, a candidate key for room would be room number and hotel number. Okay. A super key could be room number, hotel number, and type. The type is superfluous, it's not necessary, so it's not a minimal set. So a super key could be room number, hotel number, type, but that's not a candidate key, that's a super key. Candidate key is the minimal set of attributes that work. In this case, room number and hotel number work. If I take away either room number or hotel number, it's no longer a key. Okay? Now I'll take, first you had a question. Okay, and
I was just a little confused as to why you would include the type in the super key.
so a super key is simply any set of attributes that uniquely identifies. So it's sloppy. In fact, in reality, you would never include type in any key because it's sloppy. It's not necessary. So they just start with the most general definition of a key and then kind of drill down to more practical keys.
Like a super key could also just be everything about the
Bingo, I was about to say that, so great point. A super key, by definition, is all the attributes in the relation, because one of the properties of a relation is all tuples are distinct within a relation. Therefore, by definition, all the attributes in the relation form a super key. Okay, so you can have multiple, you can actually have multiple candidate keys in the same relation. So go now to the booking relation, and it turns out that now you can have more than one candidate key. Okay, so you first of all, I'd have to give you some restrictions, which is I'm not going to allow I'm not going to allow a room to be multiply booked, meaning you can't have overlapping, the same room occupied by two or more different people. So I'm not going to allow doubly booked rooms, and I'm not going to allow someone to have two reservations at the same time. So they only get one reservation at each time. And if we do that, then what might be a candidate key for booking? So basically, it's a reservation. So we want to uniquely, it's okay for a person to have multiple reservations on different dates, but they can't, for example, have a reservation today at both the Holiday Inn and the Radisson. Okay, go again, Jabril.
Everything besides the hotel number.
So let's say everything besides the hotel number.
Guest number, date from, date to.
Date through and room number. Okay, so you that might work. So you're going to have guest number, date from, date to, and room number is, yep, that should be unique. So that would be 1. Very good. So guest number, date from, date to, and room number would be 1. In fact, because I don't allow overlapping dates, you can subtract 1 of date from or date to. So, in fact, one of the two, date from or date to, ends up being unnecessary because I'm making the ranges be unique. So you only need 1 of those 2. But that by itself gives you 2 different keys. You could have guest number, date from, room number, or you could have guest number, date to, room number. Okay? But that's not it. There's more keys. There's more candidate keys. There's other ways. Pardon? So that's not enough, hotel number and room number, because you could have multiple reservations for the same room. I'm allowing them for different days. So people, you might have booked for one day and I might have booked for a different day. So you need the date as well. So hotel number, room number, and one of the 2 dates is another one. So you actually have at least 4 keys. Okay, 2 of them are guest number, one of the 2 dates, and room number. And the other 2 are hotel number, room number, and one of the 2 dates. So you actually have 4 candidate keys for booking. Pardon? So if you just had date from and date to and a room number?
No, I mean, on one of them, I think you didn't have, hotel number, date from, and room number.
You didn't. So one was hotel number, a date, and a room number. You didn't have a guest. You were right. You didn't need a guest.
Would you not need a guest?
If you have a hotel, if you just have a hotel number, if you just have a hotel, say Holiday Inn, room 303 on August 28th, 2018, there can only be 1 person in the room. So that's unique. You don't need the guest number for it. Okay. It's not easy. I'm not claiming, it takes a little time to wrap your head around that one. Yes?
Is the booking restricted to 1 hotel, or is it
No. The booking is for all hotels in our chain.
Then wouldn't you need the guest number?
No, because generally a room is only under 1 guest, right? So if you have the hotel number, the room number, and the date from, you should be able to get the guest. Yes.
So did you say you could or could not book multiple rooms at the same time?
So I was saying that the same guest cannot book multiple rooms at the same time.
So then would you
That's not a realistic one, but it makes I want to be able to generate multiple candidate keys. Okay? So yeah, if it's a wedding party, I just blew out but I just made it arbitrarily so I could force there to be multiple candidate keys.
So if they could only book 1 room at a time, then would you even need room number as part of the, you could have a key without the room number?
No, because if you just had the hotel number and actually maybe, I think that's another one. You could have hotel number, guest number, and date from. Yeah, that would be yet another. Very good. That's yet another candidate key.
Why do you have to have 3? Could you just do guest number and then date from? Because the guest can only get 1 room.
Correct. Actually, so the candidate key is actually guest number. Let's see, is it date? Actually, maybe we don't need room number. Do we need room number? Guest number and date from. Yeah, actually, guest number and date from should be enough. You're right.
Could guest number be duplicated across multiple hotels then?
But you only allow the guest to have one reservation at a time for a certain date. I made that an arbitrary restriction.
Okay.
So you have to know when you're doing it, you have to know, it's very important to know what are the restrictions. So that's why I was careful to say at any given time, so for any given day, a guest can have only one reservation for that day across all hotels. And the second restriction was only one person in a room. Obviously, not exactly in real life, that's not necessarily right, but I was just forcing it so to prove that you could get multiple candidate keys. Okay. Let's see. So, okay. By the way, you'll notice that actually with reservations, all of those were multiple keys. In practice, you get a reservation number or confirmation number because normally we don't like to have multiple fields as our key. The reason is, remember that one relation's primary key becomes another relation's foreign key. So if the primary key is two or more fields, it's going to be a foreign key in one or more relation. Those two or more fields will get repeated in every relation where it's a foreign key. That means a lot of redundant data, and it means a lot of extra storage. So in fact, most of the time, you end up generating unique artificial keys, even for things like reservations. You might even do it for rooms, generate unique room IDs. Yes?
Simple question is, again, the idea is that you can have multiple identifications. But for the example we're using, since we have guest number and date would be the candidate key, does that make other three not the candidate key anymore?
No. All of them are valid candidate keys. That's why they're called candidate keys.
Candidate key is the minimal.
Yes, it's the minimum set required to uniquely identify all tuples.
Guest number and date.
Yes. But guest number and date too also uniquely do it, so it's also a candidate key. Okay, so it's like candidates for, we're going to vote. They're called candidate keys because we're going to now, quote, vote. We don't really, but one of them becomes the primary key, and the other become alternate keys. So from our set of candidate keys, we choose one of them to be the primary key, and the rest become alternate keys. Okay, so in the case of booking, you would probably do it based on which queries are most likely. So you probably would actually choose the primary key to be on guest number and date from. The reason is generally when someone calls in to ask about their reservation, it's their guest number and the day they check in that they remember. Okay, they're less likely to remember the day they check out, and they certainly are unlikely to be familiar with the hotel number. So you would probably choose the primary key to be guest number and date from, simply because that's the query that's most likely to get asked. Okay, and then we've talked about foreign keys again. A foreign key is essentially a pointer to a primary key in another relation. So it allows us to join information from two or more relations and extract information from multiple relations to satisfy a query. Okay, and you'll see in a moment that there is some constraints on a foreign key. Because just like we don't like, what's a bad thing with a pointer? Come on. You get bad things. What causes seg faults? Dangling pointers. So just like you don't want dangling pointers, you don't really want foreign keys that don't act. You don't want dangling foreign keys, which would be a foreign key that doesn't refer to any valid key in another relation. That would be kind of bad. Okay, so we just went through this. Okay, so one thing that I have not mentioned is that when you have attributes, it is not required for them to have a value. Okay, in this particular schema, there probably would be values for all of the attributes. But let me give you a scenario. We're a very accommodating hotel. So we let you tell us your check-in date, but you can check out whenever. So you're allowed to give us a checkout date, but it's optional. You could do that, okay? So relations allow for there to be optional attributes, meaning an attribute where there may or may not be a value provided for that attribute. It's perfectly fine to have these attributes that have optional values. Okay? Let's see. So moving on, in fact, we will now talk about that. So we talked about properties of relations. Then we normally, remember from last Thursday, we said that one of the things the database does is it guarantees integrity of data. So integrity of data means that we sometimes wish to place constraints on the data that are going to ensure that there's not inconsistency. So the first thing is the so-called null value. Remember, I just said that there are some attributes that may have an optional value. The way you denote a value that has not been provided is with null. It doesn't mean it's not the same as 0. It's not the same as spaces. It simply indicates an absence of a value. For example, a comment field. The property management company may keep a viewing relation. The viewing relation might have, can't really write there, so I'll just show it. The viewing relation might be the property number, the client number who viewed the property, maybe a date, and maybe a comment. So we might make the first 3 fields required, but the 4th field optional. So maybe the client or the realtor has no comment to make about the property. So we say the comment was optional. So in that case, if someone provided no comment, we would simply have the value null for that particular cell. That would not, it just indicates an absence of a value. Okay? And if you have a large number of nulls in a attribute, you might consider branching it off into a separate relation. We'll talk about that later. Later we'll get to talking about how you design relations. But for now, we'll just say it is okay to have a null value. The second thing is something called entity integrity. So don't worry about the word base relation yet. We'll get to that. So just pretend it says relation. So no attribute of a primary key can be null. Okay, and that should make some amount of sense because you're presuming that every attribute in that key is important to distinguishing the tuple. So if any attribute could be null, that would take away, basically, it would probably mean that that attribute doesn't need to be in the primary key. It probably is not required in order to uniquely identify the tuple. So entity integrity says no field in a primary key may be null. What does that also kind of imply? If no field in a primary key can be null, what does that imply about the attributes? Required or optional? required. So all attributes in a primary key are required. So entity integrity refers to primary keys. The next one, referential integrity, refers to foreign keys. Means we don't want to have dangling pointers. So if a foreign key exists, it either points to a valid primary key in another relation, or it is all nulls. Okay, just like a good pointer in C++ is either null or it points to a valid piece of memory. We don't want dangling pointers in C or C++. We don't want dangling foreign keys in our database. So that's what referential integrity is. Either your foreign key is all nulls, or it is matching a candidate key in some other relation. And I know it says candidate key. In practice, it's generally matching a primary key. Okay, fourth kind of constraint. So far we've seen null, entity, and referential integrity. The fourth is that you can have general constraints or additional rules on your database. So those are generally considered business rules. So on my hotel schema, when I said that no room may be doubly booked and that no person may have more than one reservation at the same time, that fell under the category of general constraints. So that was a business policy. Okay. Another example, maybe no staff member may have a salary that exceeds $100,000, or maybe no staff member may manage more than 50 properties. Those would be other examples of constraints. They're essentially business policy, but you still want to enforce those constraints in the database. Okay. So those are they're called integrity constraints. There's 4 of them. The first one's just called null. Second one is called entity integrity. Third one, referential integrity. Fourth one is called general constraints. Okay. We good with that? Okay, last concept for today. We have what we call our base relations in the database. So this is tuples that are physically stored in the database. They physically reside somewhere in the file system. We may want to create virtual relations, and those virtual relations are called views. So they do not have a physical existence in the database. They are instead dynamically derived from one or more base relations. One common example of a view is something that contains what are called aggregated information. So for example, we may wish to know the number of staff in each branch. So we may want a relation that is essentially, let's see if I can bring up the notepad for a second. So we might want to have, say, a branch. Uh-oh. There we go. Uh-oh. Not happy. Kind of happy. You can see from the fact that I'm having trouble. It's not wanting to ink. Okay. Branch, let's say branch count. So it might be branch number, say staff count, maybe average salary. So this is not a physical relation in our database. Instead, it is a view. And we are going down. It's called Crash City. Okay. But at least I was able to ink it up first. So at any rate, if we go back and look at our very first thing, back here, you can see from staff that there's some staff at branch 5, some at branch 3, some at branch 7. So they're all contained in our staff relation, but maybe the president of the company wants to know the number of staff at each branch and their average salary. Well, that information can be derived from this particular relation by adding up all the number of staff at B5 and then averaging their salary. But the relation that that president is viewing is called a view. So it is obtained by aggregating data from one of the relations. Well, you're not limited to one of the relations. You could actually join 2 or more relations. Or it could be a selective view of the relation. For example, going back again, you may want to allow the manager of a branch to see all the information about the employees at that branch, but not any information about employees at any other branches. So again, it would be a virtual relation consisting of only staff members at that manager's branch. Okay, so again, it is a virtual relation that does not physically exist in the database. Okay. So sometimes you'll hear those a view called either a derived relation or a virtual relation. Again, I will tend to use the word view, but in industry sometimes you hear those other 2 words. They always refer to a view too. So simply dynamically derived from a query on one or more base relations. So base relation physically stored in the database, view virtual relation dynamically derived from base relations. Okay, so typically is produced upon request, but it can be cached. We'll talk about that in a couple weeks. Sometimes caching a view leads to faster response times, especially if the underlying base relations don't change often. So obviously dynamic, so if the base relations change in some way through inserts or deletes, you want your views updated. So for example, if we add a new staff member to a branch and we have that view of the staff counts and average salary, we need to update that view. Okay, and as we talked about the first day, some of the purposes, they provide a flexible security mechanism so that different people are able to see different slices of the database. So for example, the manager at one branch perhaps should only see the information related to staff at that one branch. The president perhaps and several other chief officers can see all staff. And then certain staff members can't see any of that information. Permits users to access data in a customized way. So the president may want to see the staff counts and average salary. That's a custom view. Okay, can simplify complex operations on base relations. When we get to it, you'll see it basically just like sometimes in a complex computation, you create an intermediate result and save it in a variable. Maybe you calculate the numerator and denominator and put them in 2 different variables. Sometimes you use a view essentially as an intermediate variable to simplify operations. Okay, and that was just to give you an example. Then there are some restrictions on updates. So, of course, when you update the base relations, you should be able to update the view. You can't always, though, update the view because sometimes the underlying base relation cannot be updated. I'm not going to, well, let me give you an example. So let's say that I try to let's say as president, I don't like the fact that the average salary is $50,000. It's too high at branch B1. And I arbitrarily say, okay, I'm changing the average salary at branch B1 to be $45,000. How do you map that back to the underlying base relation? I mean, you can't just cut everyone's salary by 5,000. That won't change. Maybe it would. Probably would, but that might not be the way that you want to come to an average salary reduction of 5,000. So sometimes when you make a change to a view, it's not at all clear how you would update the underlying base relation. So there's a whole bunch of restrictions on how you can update views. Okay, and in fact, in this class, we're not really ever going to do it. So you just have to kind of know what those cases are. So generally, you can only update a view if there's a single base relation underneath it. Once you have multiple relations forming the view, it gets a lot more complicated. So that's essentially A and B are the same. C is what I just showed you. If the view's columns were formed by aggregation, it really doesn't make sense. There's no way when you update an aggregated number to map it back to the base relation, so you can't update it in that case. Okay? So that's pretty much it with views. Any questions about that? Okay. So in 12 minutes at 1:50 p.m., at 2 p.m., the quiz will become available. Make sure you do it by Thursday at 12:30 p.m. So it's due 10 minutes before the start of class. So don't send me email on Thursday after class saying, wow, I forgot about the quiz, because I'm reminding you right now, make sure you do it in the next couple days, okay? There's no homework until next week, so don't worry about homework for the time being.